So we were talking about the n-type doping, okay, and I told you that if you give the sufficient amount of energy, like this much of amount of energy, then electrons from the phosphorus atom will be breaking up from the phosphorus atom and will be moving to this conduction band, okay. So you know the binding energy was around 0.05 electron volt, okay. So this was the energy which we needed to break this electron from the phosphorus atom, and after if you give this much of energy, this electron can move to the conduction band, okay. So if you see the energy band diagram for this n-type doped semiconductor, so when we dope the semiconductor with the phosphorus or the any n-type dopant, then you can see this is the energy level they create. So this is the energy site which the phosphorus atom will be creating, and the electrons initially, this is the electron initially, which is the fifth electron, and initially this electron is local to this energy level, okay. And now if you give this much of energy, let's say at room temperature, they will be gaining this much of energy, okay. So after gaining the energy, the electron will be moving up to the conduction band, and we will be remaining with the hole at this energy site, okay. And sufficient amount of doping is the 10 to the power 18. So we dope with 10 to the power 14, between this 10 to the power 14 and 10 to the power 20, okay. This much of the doping we call the considerable amount of doping. And if you, let's say, are doing the 10 to the power 18 atoms per centimeter cube, okay. So this is the concentration which you are mixing up into the silicon crystal, intrinsic silicon crystal. And let's say at room temperature 100% ionization are there. 100% ionization means all of the atoms are giving up their electrons, okay. So all the electrons are gaining sufficient energy and moving to the conduction band. Then this much of the electrons, 10 to the power 18, which we are mixing up, this much of the electrons we will be getting into the conduction band, yes, at the room temperature, okay. Don't forget, it is not the case at T is equal to 0 Kelvin, because T is equal to 0 Kelvin, they will not get this much of the energy. But if you increase the temperature, and we often talk about the room temperature, then they can easily get this much of energy, okay. So that is the case. Now remember, we have not disturbed the whole concentration in the valence band, but do you think what will be the concentration of the valence and these holes in the valence band? And initially we had the 10 to the power 10, yes, at the room temperature. At the room temperature in the intrinsic semiconductor, this was the hole or the electron concentration, yes. But now this will be the different, and I will be talking about that this will be the less than 10 to the power 10, the whole concentration, okay. And let me tell you one more thing. So initially we had electron and hole equal into the intrinsic concentration, and it was equal to the 10 to the power 10 at T is equal to 300 Kelvin, okay. So at T is equal to 300 Kelvin, this much of the valence covalent bond will be breaking up, and you will be get this much of hole and the same amount of the electrons in the conduction band and the valence band, okay. So this was the initially intrinsic concentration. Now, so we had 10 to the power 10 electrons in the conduction band and 10 to the power 10 holes in the valence band initially. Now you mix up some dopant, and the concentration of dopant is 10 to the power 18, okay. So now we will be getting 10 to the power 18 electrons more into the conduction band, yes. Now if you see, if you add up 10 to the power 10 with this 10 to the power 18, then you can considerably say it is equivalent to 10 to the power 18, okay, because 10 to the power 10 is very less compared to the 10 to the power 18. So now that's why we call that the electron concentration after the doping we will be getting equal to the amount or equal to the concentration which we have doped, okay. And that's why we call that these dopant atom overwhelm these initially intrinsic concentration, okay. And initially we had the 10 to the power 10 whole, but now we will be getting the less than 10 to the power 10 holes in the total, and we will see how much holes will be there. Okay, later I will be telling you, but this is for sure that the concentration of the electrons in the conduction band after doping and after at T is equal to 300 Kelvin, the amount of the concentration of the electrons will be equal to the concentration which we are doping up. Okay, so that's why we call it like N is equal to Nd plus. Okay, that is fine. Now let's talk about the p-type doping. So this is the similar concept. Now we will be going quickly. Now when you bring up the atoms from the third column, okay, so third column, you know, the boron and the gallium, they have the 3 valence electrons in them. Okay, so now instead of having 4 electrons, it is having only 3 electrons, so there will be one missing bond. Okay, so because it will be having the one less electron compared to the 4 valence electron in the silicon, so now it will be creating the hole instead of the electron. So now it may so happen that initially it was the case, but the electron from this bond can fill up this valence state, but we will be getting hole here. Okay, so electron from there has moved to this atom and created this valence state complete, but we will be getting hole at this place, and in this fashion this hole can move around in this crystal. Okay, and after getting this electron, this boron or this dopant atom, p-type dopant atom, will be called as acceptor because it has accepted one electron, or it can accept one extra electron. Yes, and after getting this negative charge, so when it will get the electron, it will be ionized with the negative charge, and that's why we call them ionized acceptor atom. Okay, and it is the same case. Let's say the concentration of the acceptor atoms is Na, and some of the atoms will be ionized. Ionized means they will be accepting the electrons. Okay, so the total holes which will be getting in the valence bond is equal to the ionized acceptor atoms. Okay, this is the same case. And if you see the energy band diagram for this p-type dopant, p-type semiconductor, then you can easily see this is the same binding energy. So initially this was the hole. Okay, this was the hole initially, and the p-type dopant atom will be creating this energy level. Okay, at 0.05 electron volt. Okay, now what may happen if you give the electron from the valence bond to this atom, this dopant atom, then we will be getting hole in the valence bond. Yes, and this state will be completed. Okay, so you just look at this electron from the valence bond will be let me remove this. So electron from this valence bond has moved to this atom energy level. Okay, so the atom's energy level is this energy level. Okay, so we will be getting the holes in the valence band. Okay, and the amount of the holes, the concentration of the holes will be getting is similar, equivalent to the concentration of the dopant atom. Okay, so this is at T is equal to 300 Kelvin. So this is not the 300 Kelvin, but at 300 Kelvin they can get this much of energy. Okay, so the electrons from there can move to this energy level. Okay, so they will be needing the energy. So at 300 Kelvin they can get this much of efficient energy. Okay, so let's talk one more fact. So initially, if what may happen that if this binding energy is so high that at T is equal to 300 Kelvin we are not able to move this electron from this energy level to the conduction band, then we call them deep donors. Okay, so for the silicon it is not the case, but there are donors or the acceptors which creates the energy level at this level or this level. That means from very deep from these energy levels. Okay, so that's why we call them deep donor or the deep acceptors. But in the case of the silicon, we are having the shallow donors and the shallow acceptors, because we only need the 0.05 electron volt, which is very near to the valence band, valence energy levels and the EC energy level. Okay, but it may so happen that some of the donors will be creating this energy level so far that binding energy is too much compared to the energy they can get at room temperature. Okay, then we call them deep donors or the deep acceptors. Okay, okay, that is fine.